Hi, my name is Daniel Vargas and my teammate is Gustavo Castillo. Our project is the design and development of an application for data reception through an OCC system. Okay, in the era of information and connectivity, mobile technology has become an indispensable tool in people's daily lives. The continuous advancement of mobile technology has paved the way for the creation of innovative applications that not only enhance efficiency and accessibility, but also provide unique and educational interactive experiences. Within this context, this project delves into the world of camera optical communications, also called OCC, with the aim of developing a cutting-edge Android mobile application. The proposed mobile application leverages the convergence of optics and mobile technology, allowing users to receive, decode, and visualize data transmitted through visible light captured by the camera of their Android devices, Android exclusively. This innovative approach challenges the traditional communications boundaries and provides a unique user experience beyond its practical applications. The application seeks to offer users an interactive and educational platform, enabling them to explore and understand data transmission through visible light. Okay, the problematic. The problematic. In the educational field, with a focus on optical camera communications, a fundamental issue is present. The main challenge lies in the lack of interactive and accessible tools that allow students and users to engage practically with this emerging technology. Communication through visible light being a relatively recent concept, trends to be abstract and difficult to comprehend without the opportunity for a tangible experience. The justifications. The justifications for this project lies in the growing importance of optical camera communication technology in an education and learning fields. OCC is a promising technological innovation, but its adoption hindered by the lack of interactive and accessible tools that enable students and users to understand and experiment with it in a practical manner. Communication through visible light is a relatively novel concept and therefore abstract for many, making it challenging to comprehend without a tangible experience. Objectives: design an intuitive and appealing user interface for mobile application that allows users to clearly and effectively visualize the data transmitted through the OCC transmitter. Integrate pre-established OCC signals decoding algorithms into the source code. And the last objective is to conduct functional tests to evaluate the user experience and make improvements for the application. Okay, the scopes and limitations. The scope of these projects composes the development of a mobile application exclusively designed for Android devices. The purpose of the application is to receive, decode, and visualize an integer within the range of 1 to 15, which is transmitted by an OCC transmitter located in the telecommunication laboratories of the Escuela Superior Politécnica del Litoral. The focus of this project is on the creation and optimization for this mobile application, allowing users specifically students to interact with OCC technology and experience data transmission in a controlled context. So what are we gonna do? We have a transmitter and we just need to receive this information. We are about to use a cell phone with an application that we are about to make. We already made it, the application. So we receive the data from the transmitter, the camera of the cell phone receive this data, and then decodified it, and after that it shows to the user. This is an easier way to the students or users to understand these systems. Okay.
How we did it. In the established setup, the mobile phone acts as a receiving device. The integrated camera in the device plays the critical role of capturing the light signals emitted by light-emitting diodes, LEDs, operating in the RGB spectrum. For the effective decoding of these signals, an advanced algorithm developed in the Java programming language is implemented, incorporating the capabilities of the computing vision library OpenCV. This library is essential as it provides a set of functions for advanced image processing, optimizing the interpretation of captured visual data. Subsequently, the system facilitates the visual representation of decoded data on the mobile device's user interface, allowing direct interaction with processed information. The processing of binary image offers notable computational advantage over color or grayscale image, particularly in environments where resources are limited, such as mobile devices. This image composed solely of black and white pixels, binary values 0 or 1. Significantly reduce the complexity of necessary calculation compared to color image processing multiple channel, red, green, and blue, or grayscale image handling various intensity levels. The inherent simplicity of binary image optimizes the implementation of algorithms and computational process, resulting in a lower demand or resource such as processing power and memory, both of which are frequently limited in mobile devices. Therefore, the use of binary operation not only accelerates performance, but also promotes more efficient management of available resources in such devices. The original image represents as a matrix of pixels, contains all the necessary visual information. The initial goal is to decompose this matrix into components reflecting homogeneous characteristics for a more detailed interpretation. For example, separating the image into red and blue color channels allows analyzing each channel independently. Using OpenCV, the first step in the processing algorithms involves splitting these channels into their respective matrices. Each of these matrices undergoes a series of transformations to decode the information they contain. This operation not only segregates relevant data, but also enhances clarity and precision in the obtained results. After separating the image into red and blue channels and converting each into distinct matrices, the channels are binarized. Through Java method integrate into the application code and using specific OpenCV functions, each channel is binarized based on the predefined threshold, simplifying the representation of the image in black and white for easy handling of relevant information. Since each sent message corresponds to different pixel percentage values, it is necessary to compensate for the pixel percentage information to a specific value within a range. There will be different range of pixel percentage, and for each range, a unique output value is established. For example, if there is a range of percentage from 10 to 30, and the pixel percentage of the object is 25, which falls between 10 and 30, the compensate value is set at 20. Finally, to decode the information, the compensation value for the red and blue channels are used. The proper implementation of K-means algorithm culminates in obtaining an image with a sharper and more defined delineation of black and white stripes. Subsequently, a meticulous cropping of the image is carried out, paying special attention to the contours, specifically the stripe located at the edge. This step is crucial for the detailed evaluation of image compensation. Finally, the decoding phase takes place, an essential analytic process that transforms visual information into an interpretable and meaningful format. The method takes a moment to process this information. In conclusion, the project has successfully achieved receiving, decoding, and displaying messages through optical camera communication on a mobile device with the Android operating system. User has the option to adjust the ISO and the shutter speed in the camera, providing flexibility in interacting with visual information.
So that's our project. Thanks.
Thank you.
Sure.
Certainly, in the results of this project, the application successfully captures and decodes information transmitted by the optical communication system to the Android mobile phone. The mobile app's intuitive user interface allows users to adjust camera settings such as ISO and shutter speed, optimizing the capture of the red and blue light separately. This capability is crucial for decoding information embedded in color patterns. The implement algorithms efficiently process the captured image, extracting meaningful data from the distinct color channels. The app's functionality includes real-time decoding on the transmitted signals, provide users with clear and effective visualization of the receiving data. In conclusion, the results showcase the successful integration of OCC technology with an Android mobile application empowering users to interact with the comprehensive transmitted data efficiently. The project's outcomes highlight the importance of OCC in modern communication systems and its potential impact on educational contexts.